thing that you may have heard of is asynchronous compute is a thing that happened with DirectX 12 and Vulkan. With AMD's graphics cards, if you were throwing stuff down the graphics queue and you weren't using all of the all the units on the card, if you threw stuff into the compute queue at the same time, it would use the spare pieces that were left over the graphics queue wasn't using and do the compute jobs on them. So I think Doom was the first thing to use it, the new version of Doom on DirectX 12 and on Vulkan. And it meant that on AMD's cards, they could schedule a load of post-processing work when the game was running. So there was no, we have to wait for this to finish. It was so much faster that we able to utilize all of the bandwidth of the internal of the graphics card. I think even the latest NVIDIA cards have started to pick this up now as well. They can schedule different things, interleave different things at the same time. So it's exposing a lot more of the power of the graphics cards to the application as opposed to trying to hide them inside this OpenGL API.
Is that scheduling the driver or the hardware?
The schedulers, the good question, sorry, the question was if that's scheduling in the driver or hardware. It depends. There's, at least with the AMD Radeon, the kernel driver currently does the scheduling in parts, but the hardware has the capabilities as well. It moves depending on which GPU you're looking at. So just one area that's good to know about is, so I said GLSL is this big, hey, C processor. Oh, I need to actually run all this stuff just to make it into the binary I need. So they decided to address this problem by introducing a different sort of style of shading language called SPIR-V. It's binary formatted language. It's open standard. It's a separate standard to the Vulkan standard. It's also used by the OpenCL thing, and there will be OpenGL extensions to allow you to use it with OpenGL. If people are compiler or intermediate representation knowledge, it's SSA based, which means it's single static assignment, which is a form of representation that makes it easier to optimize things. So it's more like an assembly language thing compared to the GLSL C level language. If you've ever looked at DirectX, it's got HLSL at the top level, but when you go to the driver level, it's got this HLSL bytecode. And it's in that sort of area. The idea behind this is you don't write shaders in SPIR-V. You still write your shaders with GLSL or HLSL, but you convert them to SPIR-V when you build your application, not every time you run your application. Yeah, so the idea of offline generating the SPIR-V and then giving that to the drivers still have to compile it, and there is still caching. Again, the caching is explicit. The application is told, here's the result. You can build a cache. Here's a SHA of it. You know, it's all explicit. Again, the application can control the caching. It's not hidden from it, which in OpenGL, all the caching was all magic, and you didn't even know if it was there. Drivers didn't even have to have it. But the only way to make things fast was to cache things. So it's an interesting diversion. SPIR-V, it has problems like anything. It's not perfect, but it's a lot easier to work with at that level rather than having to write a C preprocessor. So what does that mean from my point of view on Linux? From a driver developer, for somebody that wants to make Vulkan work on their graphics cards. Well, for a start, compared to writing an OpenGL driver on Mesa, like if you want to add something, all of the error checking had to be done first, and all of the tests for the error checking had to be done. We don't have to error check, which is a bit scary, and sometimes you still find yourself putting in error checks and then going, I'm probably not made to do this. The validation layer should be doing this. I should be doing this in the validation layer if it's not already doing it. Yeah, you'll still stick asserts in and things because you're writing code and you know crap's going to happen and you haven't done things perfectly. But yeah, it's kind of a, oh, we're out there, we're going fast. So the command string creation is explicit. So this is how the threading it works out. The threading is, instead of you going, I'm writing stuff, send it to the GPU, you go, okay, I wish to decide in advance what I'm going to write, and I'm going to tell you explicitly every single thing I want in this command stream, and it will build your command stream. And then when I am ready to tell the graphics card that I wish to use this command stream, I will submit it. And the submission is the only thing that is single-threaded. That you have to submit your command streams in a certain order so that they get into the graphics card in the order you wish. But building the command streams is a big, it's a very CPU-intensive job and so on. But with GL, there was so much overhead between what you got at the API and what you got at the command stream at the end. The overheads were too large. Whereas with this, you go start a command stream. You put all the startup data in it. The command says draw. You put this 10 bytes for a draw in it. You just build it up byte by byte or word by, it's probably word by word, I suppose. But it gives you a lot more control over how large the command stream. It doesn't actually matter. You'll just grow it till the application says I'm finished, and then you record that, and that's static from then on. The whole way it builds pipelines, so there's a concept I haven't really mentioned, but if you look at OpenGL, if you've got a shader in OpenGL and GLSL, there's a whole bunch of other things you can do to affect the hardware or how that shader works on the hardware. So you may switch on blending and suddenly, or alpha testing, these are common features. You may switch those on, but the hardware has no native support for something like alpha testing. So how does the hardware do alpha testing? It hacks your shader, and it adds a big bit of code into the bottom of your shader. And you get into this problem thing called shader variance, where you end up, for every single GLSL shader you get from the application, you could be generating 20 or 30 different actual hardware shaders dealing with all of these cases. Some apps are good, some apps are bad. You get this crazy explosion that you can't see from the outside. So you have no idea how much time it's taking up, or when it's a slow path, it might work on one driver, it might be slow on another. So Vulkan has recognized this as well and has designed a sort of a hierarchy of objects, but they're all static objects. So when you give the shaders to the driver level, it has all the information it needs to know to build the right shader. There's still occasions you might have one variant or two variants, but you have all the information at that point to build the one shader you need to make the thing work, which again cuts down on your CPU overheads quite substantially. So writing a driver for this is actually quite simple. It's a lot easier because it's very, okay, I have to do this thing. That means I have to put these bytes in the command string. This thing, these bytes. And it's just, you just do that a lot. And other pieces are slightly more complicated, but it is very quickly, here's the API, here's the command stream, or here's the API, that is in a buffer. There's no spending time messing around and figuring out what all the weird corner cases are. So as a driver developer, I quite like it. It made my life a lot easier. But where did we go? So Linux support, where are we today? First of all, there are, of course, proprietary closed source drivers. I will give them a mention because they do exist. Not in my world, but other people live in the real world, I suppose. So you may come across these things. Stay away, no. But yeah, so of course NVIDIA are NVIDIA. So NVIDIA have produced a binary driver for Vulkan. It comes as part of their standard Linux driver package. It still uses the loader and the layers and all that sort of stuff. I can't actually say much about it because I've never run it. So that's, but it does exist, and it seems to be pretty good because NVIDIA do like to put a lot of effort into these things. AMD has a closed source driver. I think they launched it just after the launch date. It's part of their AMD GPU Pro package. They promised, and I always believe when people promise me things, that they will open source this any day now. A year ago. So, yeah, I'm sure they will, but I'm sure it won't be the greatest process in the world. I'm not sure how it's going to get open source. It might be a throw it over the wall. It might be a, we don't really want to take things from outside the company because how could you know how our hardware works type of attitude you get a lot with people. It's like, oh yeah, we're the only people that could ever design anything that could work on our hardware. You're never going to make it better. And then you send them a patch that makes it better and they're like, oh, we don't know what to do with this now. We haven't got a process. So it's up in the air. I'd have loved to have seen this when I submitted this talk. I thought when I submitted this talk that I might have this driver by now, but I quickly realized that wasn't happening. But I'll get to what happened. But so when Vulkan released, these two drivers came out. But thankfully, keep doing that. The Intel Linux team, the guys who were responsible for the OpenGL drivers in Mesa on all of the Intel hardware, had stepped up internally in Kronos before the release date and actually had started working on the driver. So there was a team of, I think it was Jason Ekstrand, Christian Hogsberg, I think was it Chad? Was it Versace? Those guys had done, and a bunch of other people, but the main three leaders were those. And they started this in working on this May 2015. They had I should have written down what date day one was. I have on my slides. I forgot to write down what the date was. But they had an open source driver on the Vulkan release day, and it was conformant with the conformance suite that was available on the Vulkan release day, which was very impressive. It was an open source driver written from scratch in Mesa, and it was more conformant than the AMD because they hadn't actually done conformance at that stage, and it was up there with the NVIDIA. So it was a really good example of how two or three, I was like 3 and 3.5 people over 8 months, I think was sort of the team size. It varied who came in and out of it, but how you could deliver something like that with a small team instead of hundreds of people and not deliver it at all. So it's an impressive piece of work. I'll get to a bit of a detail now about how it sort of works. If you look at this, you'll see these are sort of the components of what an open source Vulkan driver has ended up looking like, pretty much because this is how ANV worked. So why do anything different if it worked? At the top level, the two components that are, these are sort of the